So this question, we're just going to kind of dive right in here. This question says, consider the reaction represented by the equation, right? And we have this equation in front of us. The first thing we should check is that it's balanced, because the coefficients make a big difference in us solving for the reaction constant, or the equilibrium constant. So I see an iron on both sides, CN on both sides. So it's balanced fine. This says in trial 1, 6 molar iron and 10 molar SCN are mixed at a certain temperature and at an equilibrium concentration. And at equilibrium, the concentration of our product is 4 molars. So what's the value for the equilibrium constant at this equation? At this reaction. So K is usually concentration of the products over the reactants at equilibrium. But in this case, we only have one of my concentrations at equilibrium, and we have the other two concentrations that are starting concentrations. So those are not equilibrium concentrations. Do we understand the difference? Right? This is how much we start with, and then it tells us the concentration of our product at the end. So it's not giving us enough information to go ahead and solve for K just yet. Okay? So we're going to set up what is called an ice table. So I'm going to flip to that next slide because I got it a little bit set up. I don't know if I have it on your side. Okay, I have it solved on your side. I almost want you to just ignore the solved one and let's rewrite it, or however you want to do that is fine. But I'm going to, your book, I felt like breezed through the example, but I actually want to walk through the example so that we see what's happening here, okay? We're going to set up what's called an ice table. And ice stands for initial concentration, change in concentration, and equilibrium concentration. So we're going to set up just like a little table for ourselves to kind of figure out what was the initial, how much did the concentration change, and then that results in our equilibrium concentration. Okay? So I set up my table to say I know my initial concentration of iron was 6 molar. My concentration of SCN was 10 molar. And those were the only two starting reactants we had. So my concentration of FeSCN had to have been 0 at the beginning. Would we agree with that? Yeah, go ahead.
Always going to be true?
No, it's not always going to be true. Sometimes you'll have a concentration to start here. Sometimes this one will be 0 and you'll just start with one of your, there's just a lot of different things that could happen. So you're going to have to figure out what those parameters are and put them in. But this ICE table, ICE, that will apply to all these different types of problems that we could do. Okay, so I want you to look here at our coefficients. What's the ratio of our coefficients in this problem? All 1 to 1 to 1, which means whatever concentration leaves my reactants, it's going to be at the same rate. Okay, so they're going to lose some amount of concentration at the same rate, right? Moles, my amount of moles that would transfer to my product would be the same rates for iron and SCN. If there was a 2 here, which would leave at twice the rate. So there would be like a minus 2x there. Okay, but it's not. They're 1 to 1. So that means that whatever concentration I'm losing of my reactants is happening at a 1 to 1 rate. The same is true for what I'm gaining in my products. So these reactants are losing concentration, which is why we chose a minus x. And my product is gaining concentration, which is why I chose a plus x. Does that kind of make sense so far? Again, if this was a 3, it would not just be plus x, it would be plus 3x. Okay, but it's not a 3, so we're just going to have it at plus x there. Okay, we feel comfortable? Yeah, go ahead, Hope.
How do we know which ones are losing?
Okay, so always the reactants side of my reaction is the losing side, right, is subtracting, and always my product side is gaining. Okay, even though we know the reaction is reversible, we still get the privilege of just looking at our original reaction and always calling this side the reactants and this side the products. Okay? Yeah, Cooper.
Would it still be subtracted even if it was at 0 to start?
Yeah, no. If one of these was 0, we wouldn't be subtracting because we wouldn't have anything there. Yeah, good question. Actually, I kind of misspoke. I don't really think this one of them could be at 0 because then the reaction wouldn't really take place. Right? That was kind of my fault. I don't know why I said that, but okay. So now we've got to figure out our equilibrium concentration is going to be 6 minus x and 10 minus x. And this, we know, they told us in the problem that our concentration here, our final, my equilibrium concentration of my product is 4. Okay, but didn't we say that this was going to be essentially 0 plus x? So what does x have to equal? It has to equal 4. And so now I can come over here and say my equilibrium concentration of iron is 6 minus 4, which is the same as 2 molar. I can come say 10 minus 4, which is 6 molar, and this concentration is 4 molar. You see how that kind of works out, right? It came to us already because we were given this information. Okay, it doesn't always happen like that, but this one is kind of nice that it came out with nice, pretty round numbers. Okay, but that wasn't really what it even asked us. It asked us for K. So now we need to go ahead and set this into our law of mass action and say the concentration of the product over the concentration of both my reactants. Is there going to be anything that's not to the first power here? No, because all of my coefficients are ones, right? And it's always products over reactants. So 4 divided by 12 should be 0.333 molar. Nope, not molar. Ugh, so silly. Because what's the unit for K? There is none, right? We don't include a unit for K there.
That's so unfinished.
I know. Okay. All right, we feel okay about setting up the table? Sometimes and soon, it's going to get more complex than that if we don't know this number, right? If we have to set up this as x, then we're going to plug this, and this into my K equation, and that's where the quadratic's going to come in. So it's going to get spicy here in just a little bit, okay? Like on the next one. All right, let's try it. This one says it's the same reaction. So my second trial of this reaction has different initial concentrations, and it says it's at the same temperature. So what is that? What the same temperature part of this is really key, because what does that mean can be the same for me? My K value is the same. Very good. So at the same temperature, I know my K is equal to 0.333, and that's going to come into play a little bit later. Excuse me. So it wants our goal here to find out what is our equilibrium concentration of my product. That's our goal here, equilibrium concentration of my product. So I need to set up an ice table. So I'm going to give myself a little bit more room here. And we're going to set up an ice table, ICE. And I just go right in order of the reaction. That makes the most sense for me, and it keeps me organized. So initial concentration of iron is 10. Original concentration of SCN is 8. And my original concentration of my product is 0. My changes are going to be minus X, and plus X, right? Because we're all 1 to 1 still. But now our issue is that really we're solving for this guy, right? If we put a equilibrium, right? We're really solving for this guy, but it didn't tell us like it did in my last one. So all I get to do is just leave it as an X for right now, because 0 plus X is the same as X. Would we agree with that? Right? Really, I'm going to put this whole thing in 0 plus X, but that's just X. My equilibrium concentration of SCN would just be 8 minus X, and then of iron would be 10 minus X. So I'm not able to just take a guess here right now and figure out what my final concentration is. I have to solve. But this time I'm given my K value. So now we're going to have to do some math, right? We're going to come up and set up K equals all that stuff, right? But I'm going to use 0.333 as my K value. Okay, so I'm going to rewrite that with K and give myself a little room here. All right, so K equals 0.333 equals the concentration of my product, which we only know right now as X. And does it need to be X squared or anything like that? No. Okay, and so the products of my reactants are 10 minus X and 8 minus X. Okay, so do we see like a little problem, like, or do we see the math like coming down here? Okay. There's probably a more efficient mathematical way to do this, but I don't know. I'm going to go ahead and FOIL this. right? And then I'm going to move it up. So I'm going to go ahead and start doing that. And I'm going to hold on to this x right here for just a little bit, and we'll move that over eventually. But I'm going to go ahead and FOIL this, and then I'm going to multiply it up to that side. So work through that as we go. I'm going to make my ice table a little smaller, give myself some room. Okay, so that leaves me with 0.333 times 80 minus 8x minus 10x plus x squared, and all of that's equal to x. Okay, so we did all this math to get our quadratic set up, and so now I've got my a term here, my b term here, and my c term right there, right? The a term is what goes with x squared. So now we come to our calculator, and we're going to take a big shortcut, right? Rather than having to solve the quadratic by hand, we're going to come to our calculator, since we programmed it in there, and we're going to say the first one is 0.333, enter, the next one's -7, and then positive 26.64. Yeah, right. So we were given two values. That's a good question. I want to wait till everybody gets to that point, but then we're going to talk about that. Okay, because did you plug it in your calculator? Did you get two values? Because when you solve the quadratic, it's essentially factoring, right? You have two values for that. And so my two options that came out were either 16 or 5, right? Could it have been 16? Can I take 10 minus 16? If I did, I would end up with a negative concentration of my initial. That you can't have negative concentrations of things. So that automatically eliminates that. That's usually going to be the case. What if one of our outcomes would have come out negative? It wouldn't have worked either. So you can automatically eliminate one of those, right? And so I know that my x, all I did right now is solve for x. And so we can come over here and say that since our equilibrium concentration happens to be equal to x, I know that my final concentration of FeSCN plus 2 is 5 molar. And same exact temperature, so we're going to assume our K value stays the same. Okay, if you want to try guess and check here, you can, because it's going to be a whole number again. But I'm not going to suggest that method often, because very rarely does it turn out to be a whole number.
Still using 0.23?
What'd you say?
Are you still using 0.23?
Yes.
I don't like these numbers.
Something went wrong with mine. Shoot. Did I foil that right?
I think I have the same numbers after you.
What'd your quadratic come out to be?
3.323 minus.
I mean, when you actually solved the quadratic,
Like 3.323.
So I just plugged something in my quadratic wrong. Silly. -5, 12. Oh, so silly. Okay. So x was either equal to 12 or 3. So it had to have been 3. And so we come over here. Remember, this, I think it's going to be simple for us to just like solve this and think my problem's over. Right? But we have to know that 3 is equal to x. So if we come back here and this would have been 2x, or something plus x or something minus x, we would have had to do that math also. But it just happens to be that our equilibrium concentration that we were looking for is that. So FeSCN is equal to 3 molar. The equilibrium constant equals 5.10. Calculate the equilibrium. Do you know what this means? Yeah, it just is abbreviation for concentrations. Okay? Calculate the equilibrium concentrations of all species if 1 mole of each is mixed into a 1 liter flask. Okay, so it's making you calculate initial molarity. Do we see that part? All right, 1 mole in 1 liter, that makes it really easy, but it makes us do that. I think my equation is balanced already, so we're good to go there. When it tells us my equilibrium constant equals 5.10, that means K, right? K is equal to 5.10. So we'll need that in a little bit. Okay, let's do our ICE table for this. Initial concentration for all of them is just 1, right? And we've got 4 species here, 4 different chemicals. Okay, as I walk through, it's going to be minus x, then what? Plus x, because none of mine have coefficients in front, right? A coefficient becomes a multiplier here on how fast this concentration will change. Okay, so now this becomes 1 minus x, 1 minus x, 1 plus x, 1 plus x. So let's plug that into our K equation. 5.10 equals 1 plus x. And aren't I just going to take 1 plus x again? Okay, so can't I just say this is 1 plus x squared? Okay, I could. And I'll show you why I'm doing that. On the bottom, aren't I going to just take 1 minus x times 1 minus x? Which is the same as that squared. So now if I have a square in the numerator and the denominator, what can I do? I can just do this. Square root that whole side. Square root that whole side. Right? That's going to save me so much time with FOIL and all that kind of stuff. If I have a square on the top and square on the bottom, I can square root that, and I'm going to be left with square root of 5.10, which is 2.26 equals 1 plus x over 1 minus x. Right? Because really I'm just getting rid of the square here. I'm not actually taking the square root of 1 or square root of x, right? Does that part make sense? Okay, so now I've got to do some, fancy math to get rid of this, but I'm just going to move this up. Okay, so times 1 minus x. So that gives me 2.26 minus 2.26x equals 1 plus x. And now I'm just doing really basic algebra to solve there. All right, I'm going to subtract 1 and add this over. So that gives me 1.26 equals 3.26x. And that means my x value is equal to 0.387. Okay, would we agree with that so far? So is that my concentration of each species? It is not, right? Because that's just my x value. So what I have to do here is I need to bring that x and plug it in for each of those, right? And so that means the concentration of CO and the concentration of H2O, right? Those are both of my reactants, is equal to 1 minus 0.387. Okay, and so that's 0.613 molar. And then the concentration of my products, CO2 and H2, is 1 plus X, so 1.387 molar. Okay, so I got my X about 1.53. I don't know if that's similar to what you guys had. Okay, so that means the concentration of H2 and the concentration of F2 would be equal to 2 minus that number. So 2 minus 1.5 gives me 0.47 molar. Okay, and that means the concentration of my product, HF, is equal to 2 times 1.53 plus 2, which would give me 5.06 molar. The next one uses the same reaction, but it has different initial concentrations. Again, you have to calculate your initial concentrations because it gives us moles and liters. I'm going to warn you right here that it's going to have to involve the quadratic. Okay, so you're going to have to end up doing the math to solve the quadratic. So I'm going to give you a few minutes head start, and then I'll get it up here on the board for you to check here. But I want to see how far we get on our own. You guys already done? Yeah? What'd you get for your X value? All right, I'm going to skip ahead if you guys are already done then. What'd you say? Right, we're close here. I had my quadratic equal to 111x squared minus 345x plus 230 equals 0. Okay, because this guy right here would equal 4x squared. And so to get my quadratic set equal to 0, I had to subtract that over. Yeah, because it's that's going to make this squared in my K equation. Yeah, okay, so that's why I have to end up subtracting that to the other side. So that's going to make it just a teensy bit different. Okay. So yeah, we're right. Our X came out to be 0.968. And really, it gave me two options. 2.14 was my other option. And it couldn't have been 2.14 because if I take 1 minus 2.14, it would have given me a negative negative equilibrium concentration, and we can't have that. So X is 0.968, which means all my concentrations are 0.032, 1.032, and 1.936. A 2-mole sample of ammonia is introduced into a 1-liter container. At a certain temperature, ammonia partially dissociates according to the equation. At equilibrium, 1 mole of ammonia remains. Okay, so we're going to have to include an ice table here as well. Right, but we were only given, moles and liters and moles. So we've got to do the calculation. So my reactant, which is ammonia, starts with a concentration of 2. And then we've got 0, 0. My change would be minus what? Minus 2x. And then plus x. And then plus what? 3x. Okay. It says at equilibrium, 1 mole of ammonia remains. So that means my equilibrium concentration here is 1. So do I need to bother going through the whole K equals equation? Or can I just use this information here to solve for X? I think you can just do that, right? You don't need to go through plugging it in for k if I know that 2 minus 2x equals 1, right? Minus 2 gives me -1 equals -2x, so x is just equal to 0.5. And so that, calculate k, that gives me the ability to find out my concentration here is just 0.5 and my concentration here is 1.5, right? And I guess I even misspoke here. I couldn't have even used my k equation because I didn't know what k was, right? That was my overall goal, so I couldn't have even gone through that. I had to figure that out first. So now to solve for k, I'm going to take 0.5 times 1.5 to the what power? Third power over 1 squared. Whoa. And so I get a k value equal to about 1.69.